Hello everyone, at this part we're going to introduce the WLAN basics. What you can see here in the figure is the OSI reference model. And among all these 7 layers in the model, 802.11 defines the physical layer and MAC protocols. Physical layer is easy to find, it's right here. While MAC protocols, you can think it's a sublayer of the data link layer. And even in the TCP IP reference model, it's the same. MAC layer is a sub-layer of the data link layer. And no matter in the wired or the wireless network, since they are using the same reference model, but only the standard is different. So you can see in the wireless network, it's 802.11 MAC, means the MAC layer is defined by 802.11, while in the wired network, since we are using Ethernet, so the MAC protocols are defined by 802.3, it's Ethernet standard. Okay, after knowing the MAC layer, next let's see the WLAN signal modulation technologies. WLAN signals are modulated and demodulated using spectrum spread modulation techniques. And about these techniques, you can see 3 features here. The first is that the bandwidth occupied by signal transmission is far greater than the minimized bandwidth required for the data, because we have already spreaded the spectrum. So it will occupy higher bandwidth. And the spectrum spread is implemented using coding and modulation, which is irrelevant to the data transmitted. Only the transmitter and the receiver are aware of the spread. The CM spread code is used at the receiver for demodulation and despread to restore the data. So from this page, we know that the process could be before the transmitter sends out the signal, it will spread the spectrum and it will lead to higher bandwidth requirements, and the signals will be transmitted to the receiver. After receiving the signals, the receiver will use the spread code to demodulation and despread. In this way, we can restore the data. And after knowing the process, what are the techniques we use? Spectrum spread techniques are DS, direct sequence, FH, which is frequency hopping, TH, which is time hopping, and trip, and OFDM. Among all these techniques, DS spectrum spread and OFDM are mainly used in WLANs. No matter which technique we use, they will bring us some features. The first feature is strong anti-interference. And next is multi-address communications. We can use different codes between different transmitters and receivers. So in this way, we can distinguish them to achieve multi-address communications. Next is secure, because normally after using this kind of techniques, the power will be reduced. For example, in this figure, you can see the power density has been reduced a lot after spreading. So it will be harder to find them or to distinguish them from the noise. It's more secure. And last, anti-multipath interference. By using these techniques, we can reduce the interference of multipaths. Okay, then let's see. Here are some figures showing us the working principle of different techniques. First is FHSS. Each time when we send out the signal, you can see we are using different frequencies. F1, F2, F3 means frequency 1, 2, 3, 4, and so on. So we are hopping between different frequencies This is called frequency hopping spread spectrum. And then OFDM, which is standard for orthogonal frequency division multiplexing. So from the figure, we can know that by using OFDM, the signals has been divided into multiple subchannels. And in this way, we can improve the usage of the frequency. Next is DSSS, direct sequence spread spectrum. And the main point here is a PN code. By using the PN code, we can get the modulated spread spectrum signal, and it is what we will transmit to the receiver. About these three techniques, FHSS means that frequencies hop consistently according to the pseudo-random code definitions during transmission, with a carrier on a wideband. In FHSS, the 2.4 GHz band is divided into 75 1 MHz wide subchannels. The transmitter and receiver negotiate an FM mode in which data is transmitted through the subchannels. On 802.11 networks, sessions use a different frequency hopping mode each time. And frequency hopping prevents two transmitters from using the same subchannel at the same time. So there will not be collisions occur in the network. And in DSSS, data at the sending station is combined with a higher bit rate sequence, or chipping code. At the receiving station, the same spectrum spread sequence is used to restore the original signal and modulate the signal to the carrier. It divides the 2.4 GHz band into 22 MHz wide channels. Adjacent channels overlap each other. 3 out of 14 channels do not overlap other channels. Data transmitted through the 14 channels do not need to be hopped anymore. Okay, the last is OFDM. It's very important. OFDM is a multi-carrier transmission technique that divides available spectra into carriers which are modulated using low bit rate streams. The secret of OFDM having a high transmission rate is to divide high bit rate data into several alternate parallel bit streams and modulate them to several separate sub-carriers. So in this way, channel spectra are divided into several independent subchannels, improving spectrum usage. So the main point of OFDM is that it can improve the spectrum usage, and this is also the reason why it can improve the rate. Okay, and the typical standard is 802.11a, G, and N. From this figure, we can also find that it has divided the spectra into multiple carriers. You can see here we use different colors to represent different carriers. And the OFDM can provide higher spectrum usage. So in 802.11n, it uses the upgraded OFDM. And after using the upgraded OFDM, in 802.11n, it has 56 subchannels, or we can call it 56 carriers. And among them, 22 of these carriers can be used to transmit data. And this is the reason why the rates of 802.11 can be improved from 54 megabps to 58.5 Mbps. The channels is divided into multiple orthogonal sub-channels for narrowband modulation and transmission. The bandwidth of each sub-channel is less than the relevant bandwidth of the channel. And the high bit rate serial streams are converted to several parallel streams, which are transmitted through different subchannels. So about the OFDM, you should know that it can improve the usage of the spectrum. Okay, next is about the MAC layer. 802.3 standard includes a unique MAC layer, which is different from that in 802.3 standards. The coordination function is used to determine when a station within a BSS is permitted to transmit or receive data. Because in the wireless network, if two stations want to use the same channel at the same time, it could cause collisions. So we need some ways to manage them. And the first is called the point coordination function, and it's a no contention mechanism. In PCF, the AP takes control of access algorithms and grants stations permission to send data in terms to avoid a collision. So in PCF, all the stations will send data in terms and it's managed by APs. While another is called the DCF. It's a contention mechanism. In DCF, the CSMA mechanism, it has each station content for an idle channel to transmit data. Therefore, the DCF provides the contention mechanism upwards. The station with the highest priority will use the tunnel because it will succeed in the contention. Okay, and except the DCF, PCF, another type is called HCF. It's a hybrid coordination function. And in HCF, we have EDCA, which is based on DCF, HCCA, which is based on PCF. Okay, after knowing the MAC-based media access modes, then let's see the block acknowledgement. Block acknowledgement is called BA. In 802.11 standards, an ACK frame must be transmitted immediately in response to each received unicast data frame. You can see here, each time when we receive a data frame, we should feed back an ACK. Receive a frame, feed back an ACK. Receive a frame, feed back an ACK. So if we have a lot of frames, the number of ACKs which should respond is huge, right? So we have a function to reduce the number of ACKs. It's called block acknowledgement. You can see here, the frame aggregation means we have aggregated the frame, and in the aggregated frame, we can find the 802.11 headers, the data, or we can see the payload of each frame, and the FCS. And for an aggregated frame, we just use one block acknowledgement to respond. In this way, we have reduced the number of ACK frames. And about the frame aggregation, you can see here, this is an aggregated frame, and as we just said, we just use a block acknowledgement to respond to it. But in some cases, if one of the packets inside the aggregated frame is faulty, so we will ask for the transmitter to send it again. So what will happen? Actually, even we use a BA to respond. In the BA, it can ask for some parts of the aggregated frame to retransmit. For example, if here we have number 1, number 2, number 3, and after receiving it, number 1 and number 3 is good, but number 2 packet is faulty. So by using 802.11 ACK, by using the block ACK, we can ask for the number 2 packet to be transmitted independently. Okay, so not need to be worried about this. Okay, this is about the frame aggregation.